So hello everyone. So I'm Pascal Lafourcade. I come from Clermont in France, and this is a joint work with Jannik Dreier and Dhekra Mahmoud. So I will talk about MixNet, and first I want to present what is formal verification. So, okay, when you design a cryptographic protocol, how you are convinced that your protocol is good? We have seen many papers and talks present things. So one solution is you publish the protocol and wait in the next conferences someone find a flaw. Okay, so this is not a good way. What you should do, you should prove that there is no attack. So you should have a security proof in your protocol. So this is a good way. But now making the proof is very difficult. And how can you be convinced that your proof is good? So you can do the same, publish the proof, and wait someone find a flaw in your proof until the next conference. For us, the good approach is to do computer-aided security and to use a formal method and automatic to provide a security proof that your protocol is good. So this is what we'll do, and I will use ProVerif as a cryptographic tool for modeling and verifying automatic verification. So now go back to the title of the paper, shaken or stirred. So what is the idea? I will talk about MixNet. MixNet are cryptographic components that take as input messages and output the same messages in a different order. And the goal is that they are well shaken, but not just stirred. So this is what we want to do and to avoid that they are not mixed enough. And the idea of the paper is to discover a new subtle attack with automatic verification tools that were not able to perform this attack before. So first, I recall two attacks. So the first one is about a paper in USENIX 2011, which is exponentiation MixNet. So the idea is to mix this input on the left side, the public key. So the public key 1 until n, we want to mix. So for this, you give to a mixer. A mixer takes a random permutation and permute all these messages. And in order that you don't know the output, they pick a random number R1 and take the key power R1. And each mixnet from M1 to Mn does the same. So take a random permutation, mix the data that it receives, and take the exponentiation with a random number. And at the output, the random, which is a product of all the random number used, is given. And so everyone can check that the public key is inside the list by taking the initial public key to power the random and to check that it is inside the list. So you can do that. And this is used for anonymity and non-locality in for voter in the election protocols. Okay. So the question here, are the data as the input are well shaken or just stirred? And we'll see there is an attack on these protocols. So the attack is very simple. The attacker can sacrifice his input and take the input of the victim, S1, to power a random number that is nice. The MixNet mix everything, and at the output, of course, the attacker can check that the input is here and is exactly the initial value at the power R, but this is also the initial value of the other at the power A. So you can detect what is the value and where is the value in the list of the first input. So you can de-anonymize, link the information who sent the first message. So this is not what we want, and this is an attack. So this attack has been discovered in 2022, but is on a previous attack that has been existing before the existing of the protocol in 1994 by FISMA. There is another attack on a different kind of MixNet protocol, which are re-encryption MixNet. So this has been using for voting in 1994. So this time the ID is a ciphertext. So it's the Elgamal ciphertext here, where is CK here. And the attacker does the same. He sacrifices his input and compute CK8, which is CK to power A, which is described here, where you just put the random A chosen by the attacker on each part of the messages. This time the MixNet performs MixNet as usually, and at the end, the MixNet outputs ciphertext, which has been randomly shuffled, and everything is decrypted. And when you decrypt it, the attacker can make the link. And so this is part of the voting protocol. So this is how works the attack on this voting protocol. So what is the contribution? How can we find automatically these attacks? Because they are discovered by hand, and we want to do a formal method analysis using ProVerif. So we will provide a new model for mixnet, which take into account exponentiation, L-gamma encryption, because as you have seen, the second one use L-gamma encryption. And something that I have hidden to explain clearly the attacks is that each time you make a mixnet, they provide also a non-interactive zero knowledge to prove that the input is equal to the output. And we have a weak and a strong non-interactive zero knowledge proof and modeling in ProVerif. In ProVerif. We apply our model to e-voting, e-exam, and a crypto-standard protocol, and we discover some flow on these three protocols. So go to the details now, how we model it. So we first need to have exponentiation. So we want to model all the property on the left side, here, the mathematical property. And for this, we introduce the exponentiation commutation in ProVerif. And the first one is classical, is the exponentiation of 2. But we were forced to have the same for 3 exponentiation in order to discover the attack. Because as you have noticed, we have the public key, exponent, the power of A and the power of R, and so we need 3 exponentiation. We also need a signature, and we use a classical signature modeling in ProVerif. So now we have L-gamma protocol. We want to model it, and usually it's just abstract as an encryption, a probabilistic encryption. Or here, what we do, we just add the exponentiation in the encryption messages and the secret key here. And putting the exponentiation allows the attacker to choose the keys that will be used for encrypting. So this is a trick that was useful for our attack. For re-encryption, we have 2 properties. The first one is to put the random on each part, and the second one is just multiply by a g to power r on both r prime, sorry, on the both sides. And the other one is just randomize L-gamma encryption. So for this, we introduce new function in ProVerif, which we call re-enc, and exp by a random number to take the exponentiation of a cipher. So this is exactly what you want to do, and respect the mathematical property of the re-encryption mixnet. So now I go to the non-interactive zero knowledge. So we have a weak non-interactive zero knowledge in the literature. So it's a classical Schnorr zero knowledge. So what you do, you have the public key, and you want to prove that you know the secret key of the public key. So for doing that, what you take a random A, and you compute capital A g to power A. You hash this value, and this will be the C that is given in the interactive proof of Schnorr. And after you compute F, which is A plus C times the secret key, you know the secret key, so you are able to compute the F, and your proof is CF. What is the verification that is performed by the person who receives this information? You just check this equality here, making the hash of g to power F times the public key inverse minus C is equal to C. So what is working? I put the detail here. You just replace everything. You obtain this exponentiation, and here you can see that the secret key times C is cancelled, and you recover C. So this is a classical zero knowledge proof. But for this one, there is a flow, a very simple flow, which is very funny. You can construct a valid zero knowledge proof by taking A and F prime, 2 random numbers. And you generate C prime as the age of A prime, and you produce the proof, which is C prime F prime. And the verification that is above works exactly the same if you have the PK prime, a new key that is designed according to your 2 random numbers. So this is a trick, and this allows to mount the attack on the interactive protocol that we have seen. So here, the verification, you have the exact computation. There is in the literature a strong non-interactive zero knowledge proof, where instead of just hashing A, you just hash A and the public key. And this avoids the previous attack. Okay? So now we have all the ingredients, and we need to model this in ProVerif. So for modeling this property that I've described with non-interactive zero knowledge proof, we have a weak zero knowledge proof, where we just model as usually and the exponent in the zero knowledge proof, and the strong version where you see in blue that I add the public key in the hash of A. So this allows us to have a weak and strong zero knowledge proof and to see what is the difference between the two. Okay. We also have the possibility to the intruder to choose the public key, which is required in a non-interactive here zero knowledge proof. Okay. So now we have everything, and what we did first, we model exponentiation mixnet and re-exponentiation mixnet without zero knowledge proof, with weak and strong zero knowledge proof. So we discover flow for the zero knowledge, non-interactive zero knowledge proof presence, and we have flow when you have weak non-interactive zero knowledge proof, and when you use a strong, we don't have a flow. We did the same for re-encryption mixnet, and we discover exactly the same thing. So now to reach, we apply this to 4 protocols. So one is remark protocol, is an e-exam protocol that use mixnet. So we analyze all the security properties that were provided by remark, and we find that without and with weak zero knowledge proof, you have 2 attacks on anonymous marking and anonymous examiners, exactly where the mixnets were used to provide anonymity of the examiner and the marker. Then, if you change the weak by the strong, we're able to prove with ProVerif this protocol is secure. So you see that with the strong, it's very fast, but for the other one, it takes a few minutes to find the flow. We did the same for voting protocols that I have described previously, and we obtain exactly the same thing. And for Santa protocol, which is a protocol in the literature where you use anonymous shuffling, and we find each time privacy issue. And we also did this for Estonian voting protocols, and we show that there is 2 attacks for the vote privacy, so you can leak the vote of the user to someone. And this is not what we want, and you need to use a strong zero knowledge proof. So this leads me to the conclusion. What we have provided in this paper, we have provided new ProVerif models for mixnet, re-encryption mixnet, exponentiation mixnet, also for zero knowledge proof, and weak and strong zero knowledge proof for Elgamal crypto system, and we have a signature that is adapted to our model. So this can be taken for your next analysis. You can take this as a prerequisite in a ProVerif file, and you can analyze your new protocol with this new ability in order to avoid to have such flow. And we did 3 applications as I've shown. Thank you for your attention. I will be happy to answer your questions.